Hi everybody, welcome to tonight's video where we're going to be talking about graphing functions. This is actually going to be the first of many videos where we talk about the graphs of functions. That's really what we're going to talk about this entire chapter. But for now, we're just going to do a basic introduction and just talk about what actually determines whether or not a graph represents a function or a relation. And then we're going to talk about the domain and range of the function, which we've already talked about given the equations, but now we're going to talk about given the graphs. So we graph functions just like we graphed equations. We can either use a table with ordered pairs to plot those by hand and then connect them with a line or a curve based on what the equation is. And we can also use our graphing utilities such as our graphing calculators or the Desmos app or website if you'd like. But first, what we're going to do, we're not even going to graph today, actually. We're just going to look at graphs. And the first thing that we're going to take a look at is something called the vertical line test. And that's actually a fourth way to determine whether or not a relation represents a function. We already talked about mappings, sets of ordered pairs, and equations. And remember, a mapping, if it had two arrows coming from the same element in the domain, that meant that it was not a function going to two different elements in the range. Okay. With the sets of ordered pairs, if I saw an x coordinate listed twice with two different y coordinates, then that was a giveaway that it was not a function. And then with equations, if I saw something like a y squared or like a positive and negative square root of x, then that was not a function. Okay, so there were ways to tell that it was not a function from the mappings, the sets of ordered pairs, and the equations. Now there's a way to tell that it's not a function from its graph. And that's going to be something called the vertical line test. And the vertical line test says if there's any vertical line that you can draw that it crosses the graph in more than one point, then the relation is not a function. So if I can draw any vertical line here, if I intersect it more than once, if I intersect this graph more than once, then it's not a function. So you can draw all these lines in if you'd like. You just got to keep drawing a bunch of them. It starts to look a little sloppy if you draw a bunch, but you can also just think of the lines that are on the grid of your graph paper, because those are all vertical lines. Remember, a vertical line is straight up and down. There's no slope to it. The slope is undefined, right? So there's no positive or negative slope, right? It's got to be straight, vertical, right up and down. So you could draw a bunch of lines and see if it ever intersects twice. Here, none of these lines intersect twice. That's great. Now, it's important to note that it says any vertical line, not just a vertical line. So in this graph over here, if I look at it, I draw a vertical line, and it passes, right? It only intersects it once. So, in fact, I could draw a couple that are that way. But if I draw a vertical line right here, it's going to actually intersect this graph 1, 2, and 3 times, right? So I could draw a vertical line that crosses this graph at 3 different points. So this is not a function, right? So it fails the vertical line test. And if you want to think of this in terms of what we already, our other 3 ways of testing whether or not a relation is a function, these are 3 points, right? So if we were thinking of the set of ordered pairs here, I would see 3 different points with the same x coordinate, -1, but with 3 different y coordinates. This is -1, 4, this is -1, 1/2, and this is -1, -5, it looks like. So those are 3 different points that would be in that list of ordered pairs. So that would give me a giveaway that it's not a function. Same thing if this was a mapping, you'd have the -1 in the domain, and it would have 3 arrows coming from it going to different elements in the range. So that's how these are all interrelated. So there's the way to tell from a mapping, the way to tell from the sets of ordered pairs, from the equation, and then now from the graph. So those are different ways that you can tell whether or not a relation is a function. But now, once we have a function, we're going to want to interpret the graph of it. So functions, a lot of times what we're going to use them for are to model real-world data. So it's going to be very important that we're able to kind of look at their graph and interpret what these different points on the graph mean and how it relates to the data that we're analyzing. So like I said, the next few videos are all going to be talking about different ways to analyze, different properties of the graphs of functions, and what these different points on the graph mean. First, what we want to look at is the domain and range of the graph of a function. We've already talked about domain and range from its equation, or the equation of a function, but now we're going to be able to tell domain and range from the graph. So if you look at the graph that I have here, I've already set it up a little bit in terms of highlighting these arrows on the end of the graph and also labeling my axes. So remember, this is the x-axis, this is the y-axis, and the arrows point off to positive infinity and negative infinity, right? So these arrows, whenever you see the arrow on the end of something, on the end of a graph, it means it's going off forever in that direction, okay? And same thing with the graph. With the arrows on the end of the graph, it means that if I were to keep graphing, plotting points on the graph using the equation, this would go on forever in this direction. And so it looks like it might be eventually curving so that it's straight up, but keep in mind this is going to go on forever and ever and ever. So it's going to still slightly, maybe just very slightly, but it's still going to move off forever kind of diagonally this way. So it's going to move off forever in this direction on the x-axis towards positive infinity, and it's going to keep going up, so it's positive infinity on the y-axis as well. And then it's going to keep curving off this way, so it's going to be a negative infinity on the x-axis as well. So just keep in mind that this is going on forever. But now let's get back to talking about the domain and range. That kind of gives me a visual or an understanding of where this is going, but now I want to think of what are all the x values that can go in here and what are all the y values that can go in here. So it's kind of easy. It's going off to infinity and the negative x-axis and infinity and the negative, or on the positive x-axis. So my domain is going to be all real numbers. And remember, we have a few different ways to write that. We have interval notation. So I can write this as negative infinity, comma, positive infinity. And I use the parentheses because you can't like include the value. You don't have like a closed value there because it's infinity. So that's interval notation to say that the domain is all real numbers. So if we use set builder notation, we're going to say it's all x values such that x is a real number. And then we could also just write out the domain of this function is all real numbers. Okay, so that means any x value I plug in here from negative infinity to positive infinity would be the x coordinate of a point on this graph. On the y, looking at the domain, or I'm sorry, on the range, the y goes up to the positive infinity because of the arrows. That's pretty easy. But now when we're coming down here, I want to see basically where this graph stops on the y-axis, right? Because it doesn't go any lower than right here. So if you want to think back to, a set of ordered pairs to describe the domain and range, you can start plotting points or picking out all the points that are on here and kind of see like a general trend. Like if you started listing out all of these points, you would see that the x-coordinates start at 0, -1, -2, -3, so on and so forth. And you would keep listing off points where the x-coordinates would continue on off for negative infinity. Same thing over here, the x-coordinates would continue off for positive infinity. And the y-coordinates would keep going up. Here they would be at -3, here would be -2.5, -2, -1, 0, 1, 2, 3, 4, right? So all the y-coordinates would start going up to positive infinity. But what you'll notice is they never get any lower than -3, right? So here is the lowest point on this graph, and it stops at -3. There's no point on this graph that has a y-coordinate of -4, or a y-coordinate of -5, or a y-coordinate of -6, and so on and so forth. So the lowest that this gets to is y equals -3. So that tells me that the range here is -3, and I use a bracket because it's inclusive there, right? It actually includes the point that has a y-coordinate of -3, and then it goes off to positive infinity on the y-axis. You could also say the domain is all y values such that y is greater than or equal to -3. Or you could write out that the range is, I think I might have said domain here, the range is all y values such that y is greater than -3. Or you could just write that out. So the range is all real numbers greater than or equal to -3. Okay, so that's one way to think of it. Another way you could think of how to determine the domain and range is you could kind of like fold your paper up to here, and like you would, so that you would draw like a straight line that kind of cuts off and shows that there's nothing down here that's represented by this function, by the graph of this function, and see where your y value is. And then over here, you wouldn't fold at all because the arrows would be going off, so you would just say positive infinity, and then over here, negative infinity. Another way that I used to think of it was, that I always thought was helpful, is I would just always draw lines from my graph to the different axes, and I would see like, as if like the graph was like, if I were to like lay it flat onto the axes, where would it go? So like if I were to take the orange lines here and lay them down, see how it would go forever off onto the x-axis, negative infinity. All these, if I pushed this orange line up to here, it would fill in this space here. And if I pulled the orange line down with the green lines here, it would extend off to positive infinity. So that's how I would know that the x, or the domain, was negative infinity to positive infinity. Same thing with the y's. If I were to draw a line from the graph to the y-axis, like if I were to take the orange graph and kind of like push it down towards the y's, I would see that it would fill in going off into positive infinity, and it would kind of fill into here. But then again, it wouldn't go any lower than y equals -3. So that's how I would determine that my range goes from -3 to positive infinity. And we'll do some more practice problems with this in class. That's just a couple different ways to think about this or to visualize it. So real quick before we wrap up here, we'll do a couple examples. Determine if the graph represents a function, then determine the domain and range of the graph. So if you want to pause it, I'll do an explanation of this one, and then I'll move this down and I'll leave you with one to bring to class tomorrow. So pause it real quick, and then I'll do an explanation. Okay, so if you've paused it and you're ready to see the answer to this one, first determine if it represents a function. We do the vertical line test, and any vertical line I draw here is only going to intersect this graph once. So first of all, yes, this is a function. Okay, so now we want to think about the domain and range. So remember, we mark this is positive infinity x, this is negative infinity on the x, this is positive infinity on the y, negative infinity on the y. And think about what these arrows tell us. This arrow tells me that it's going to go off for infinity this way, and it's going to kind of gradually go up. So it's both of these, positive infinity on the x and y. And then this arrow tells me that it's going to go to negative infinity on the x, and it's going to keep going down, so it's also going to hit negative infinity on the y. So this one's actually kind of easy. The domain is going to be all real numbers, and you could use set notation or interval notation, or even just write it out, all real numbers. And the range is also going to be all real numbers because it extends off to infinity in both directions. So here if I used interval notation, negative infinity, positive infinity for both of these, and if you wanted to use set builder notation, remember it's for domain, it's the x values such that x is a real number, and here you'd have y values such that y is a real number. Okay, the last one here, if you'd like to copy this into your notes and try to determine Whether or not this is a function and what the domain and range of this graph are, that's what we'll start with tomorrow in class. All right, have a great night, and I'll see you tomorrow.